Hey everyone, it's Justin again. Now that you know the basic rules of exponents, you can move on to learning some more advanced rules. In this video, we're going to be looking at two more rules that allows us to use exponents on more complicated expressions. Before we get into the new rules, let's make something perfectly clear. When an exponent is on the outside of parentheses, the entire expression in the parentheses is being multiplied by itself over and over, not individual pieces of it multiplying only by themselves. What this means is that if a group of numbers, variables, and operations is all raised to a power within parentheses, the entire group is what gets copied and multiplied. You cannot just multiply the pieces by themselves. Keep the parentheses intact. That being said, let's take a look at exponent rules part 2. The first rule we'll look at in this video is the power of a product rule. This rule says that if you raise a product of multiple values to an exponent, it's the same as raising each piece to the exponent. Oh, wait. Didn't we just say not to multiply the pieces by themselves? Typically, yeah, that's the case. However, multiplication has a special property, the commutative property, which says order doesn't matter when multiplying. But what does that have to do with exponents? Well, let's look at an example. If we raise 5x to the third power, then that means 5x times 5x times 5x. Each 5x is actually 5 times x. Every operation here is multiplication, so taking away the parentheses won't change anything. It's still 5 times x times 5 times x times 5 times x, whether there are parentheses or not. Here's where that commutative property comes in. As long as there are 3 5s and 3 x's, the order of multiplication doesn't matter. So we can reorder them so that all the 5s are together and all the x's are together. And now we can say that 3 5s are being multiplied together and 3 x's are being multiplied. So the power of a product rule is based on the idea that multiplication can always be reordered. The key here is that the operation inside the parentheses has to be multiplication. This won't work if there's some other operation like subtraction. That exponent means 5 minus x times 5 minus x times 5 minus x, but that's as far as we can go with it. We can't take the parentheses away this time because it would change how the order of operations affects the outcome of this expression. In the version with parentheses, the parts inside the parentheses, meaning those subtraction parts, would go first. But in the version without parentheses, the order of operations says the multiplication parts happen first. Taking the parentheses away changes the problem. So we can't do that. Does that mean the commutative property can't be used here? Well, not necessarily. After all, we do have 3 different parts being multiplied, so we can use the commutative property to swap these orange and green pieces, or the blue and the orange, or any other rearranging. The thing is, this doesn't change anything. No matter how we rearrange the identical parts, we will get the same expression that we started with. Neither the commutative property nor the power of a product rule helped us to simplify this, because the inner operation wasn't multiplication. The next rule is called the power of a power rule, and it deals with exactly what it sounds like. What happens when you raise a power to another power? The rule tells us that in that situation, the 2 exponents will multiply together. What was that? You want to know why? Let's try an example, like 7 squared to the third power. Raising something to the third power means multiplying 3 of them together. So we have 3 7 squareds multiplying together. Each of those, however, is actually 2 7s. So altogether, we have 6 7s multiplying. In other words, 7 to the 6th power. That's the same as if we just multiplied the 2 and the 3 together. And for good reason, we're multiplying 3 sets of 2 7s each for a total of 6 7s. All right, so now we know the 2 new rules for exponents. So let's put them to use. Our first example is 2 times x squared times y to the third power, all to the fourth power. The first thing we could do here is use the power of a product rule. If we have a multiplication expression raised to a power, the exponent gets spread to each of the pieces being multiplied. Before we continue, we can simplify that 2 to the fourth power. 2 times 2 times 2 times 2 is 16. Now we still need to deal with those variable terms. What can we do with them? Well, we can use the power of a power rule. 16 is just 16, but x squared to the fourth power, a power to another power, those exponents will multiply and make 8. In the same way, the exponents on y, 3 and 4, will multiply to make 12. So by using the power of a product rule to spread the exponent across the multiplied terms, and then using the power of a power to simplify the exponents on the variables, we got an answer of 16 times x to the 8th power times y to the 12th power. For our next example, we're going to throw a couple negatives in it just for the fun. First, let's use the power of a product rule to spread the outer exponents across the inside multiplication. Negative 5 squared is a defined value, so let's simplify. Negative 5 times negative 5 would be positive 25. Notice the sign change there. A negative raised to an even power always becomes positive because each negative is multiplied by another negative, while a negative raised to an odd power will always leave the result negative. Okay, so now that we've got powers raised to other powers, it's time to apply that power of a power rule. 25 times c with exponents of 3 and 2 to make 6, times d with exponents of negative 5 and 2, which multiply and make negative 10. In the case of negative exponents, that process doesn't change. You still just multiply them. So the simplified result here is 25 times c to the 6th power times d to the negative 10th power. There actually is one additional step necessary here, but we'll come back to that in the next video. Here's our last example. This time the negative is on the outside, so let's see how that changes things. First, use power of a product to spread the outer exponent across the inner multiplication. Because the negative was outside the parentheses, it stays outside. Now let's evaluate negative 3 to the 4th power. We said in the last example that the negative inside the parentheses is affected by the exponent. But is that also the case here? If the negative is on the outside, then there's only one negative, no matter what. We can square the 3, but the negative isn't affected. If we use an exponent of 3, there will be 3 3's, but still only one negative. So for negative 3 to the 4th power, where the negative is on the outside, we multiply 4 3's, which makes 81, but since that negative isn't affected, it's on the outside, it stays exactly where it is. Finally, we can use power of a power. R has a power of 5 raised to a power of 4, so they multiply to make 20. The P actually does have an exponent on the inside. We just can't see it. There's a single p, so the exponent is 1. The exponents of 1 and 4 will multiply, and we just end up with p to the 4th. So our final answer is negative 81 times r to the 20th power times p to the 4th power. Exponent rules are getting trickier. Make sure you're practicing, because soon you'll have to be able to use all of these rules together. In the next video, you're going to learn the last 2 rules, how exponents affect fractions, and the big mystery of how negative exponents work. See you then.